Hello and welcome. Today we are having a lecture about fluctuations. And first of all, I would start with the fact that fluctuations already exist in the Gibbs distribution that I have introduced before. Let's look at it a bit more. So for the Gibbs distribution, we know that the probability for a certain state I to be occupied is given by the next formula. This is 1 over z multiplied by an exponent of minus beta EI, where beta is 1 over kBt, a reciprocal thermal energy, and EI is energy of the state. Previously, we have used this Gibbs distribution in order to determine average value of energy, and it can be given as minus 1 over z multiplied by the derivative of dz over d beta. If you don't remember how this formula is derived, please refer to the previous lectures. I think previous lecture has a derivation of this formula, and the lecture before that also has it. Now we are going to derive a variance of energy, dE, variance of energy, which is determined or defined as this difference. So first we need to calculate an average square of energy and subtract a squared average of energy from this value. I believe I also have derived this before. Okay, so now we are going to derive an average square of energy using the very same method which we have applied to derive the average energy. We need to make we calculate a derivative of this distribution over beta. And if we calculate this, so we can have the following. Well, not calculate the distribution, we calculate the derivative of this exponent. So first, we have calculated the derivative of z function, partition function, and obtained that it is equal to EI multiplied exponent minus beta EI. But if we calculate this derivative another time, okay, here is a minus sign. If we calculate derivative one more time, then we get that the second derivative of z over beta is equal to the sum over I of EI squared multiplied by this exponent. From this expression, it is very easy to obtain the expression for the average square of energy. We just need to write a definition for this average. And the definition is as follows. According to the definition, we need to multiply the probability of a certain energy to be occupied by squared energy. And this is sum over I of EI squared multiplied by exponent minus beta EI. But we also have a partition function in the denominator here, which is added to normalize probability distribution. And from this, we immediately obtain that squared average, average of energy squared is given by this expression. Okay, but the problem is that this expression depends on the partition function, and well, it's okay if you know a partition function of some thermodynamic system, then we know everything about it, including the fluctuations. But for the fluctuation, we have this formula. dE, the variance of energy, is 1 over z multiplied by minus squared average of energy. And in order to calculate it, I insert this value in this formula. So I have minus, and squared average gives me 1 over z squared multiplied by dz over d beta squared. Now we have something. But as I said previously, it would be better if we can express the various variance of energy through other thermodynamic values, but not the partition function. In order to do this, I need to calculate something which contains second derivative of z over beta. As you see, if I calculate this, then I can get something. And one of the quantities which contains the second derivative would be the derivative of the energy itself. So if I calculate derivative of energy over beta, I will get something which is needed. But more importantly, the derivative of energy over beta doesn't have any explicit physical meaning. And to have some physically meaningful value, I need to calculate derivative of energy over temperature. If I have this derivative, then it is actually a heat capacity of the system. So heat capacity at a constant volume, as usual as we do it in statistical physics, is given by this expression, derivative of energy over temperature. And we can easily express it through beta. So this. And now we expand these differentials. So now I have minus kb beta squared multiplied by derivative of average energy over beta. And now I'm going to insert again the value of average energy into this expression and obtain the expression of CV as a function of partition function. So I'm going to express CV through the partition function. CV through Z. So I insert that value of energy. Now I have minus kb multiplied by beta squared multiplied by d over d beta of minus 1 over z times dz over d beta. Okay, now I have some kind of a quantity which can be calculated using well-known rules for calculating derivatives. I can apply here chain rule, I can apply here multiplication rule, and get the result. So let's do it. So here is a straightforward calculation. I just expand this. So, okay, this factor kb beta squared will be always with us. But first of all, we can take minus out of here and eliminate this minus. So minus by minus give us plus. So I can omit this minus here. This is the first step. And then I open a bracket and calculate the following. Using the multiplication rule, I get d over d beta of 1 over z multiplied by dz over d beta. So I apply this derivative operator to the first factor of my multiplication. Then plus, again, 1 over z multiplied by the second derivative of z over beta. This is the result. Then what I have here, I need to calculate this derivative. And this derivative can be found using chain rule. Okay, I have almost no space here. I will start here, maybe I will proceed with that on that blackboard. So let me see. So to calculate this derivative using chain rule, I first of all calculate derivative of 1 over z. That will give me minus 1 over z squared. Then I multiply by dz over beta. And again, dz over d beta, as I have such factor there. So altogether, it gives me dz over d beta squared plus 1 over z multiplied by the second derivative of z over beta. So now I have quite a complicated expression, but if I look at this expression, I see that this expression is quite similar to this one. And it makes it, well, it should be quite easy for me to find the correspondence between the heat capacity at constant volume and the variance of energy. So I just insert this variance of energy here and get the result. Okay, so this is 1 over z, or multiplied by the second derivative, this is this term, minus 1 over z squared multiplied by derivative squared, this is this term. So exactly what I have here is kb multiplied by beta squared times variance of energy, dE. Okay, from this we can easily find variance of energy, and I'll write it there. Variance of energy is Cv over kb beta squared. Okay, I think it would be better to express it in terms of temperature. So as this beta is 1 over kBt, and then I get this, which is Cv multiplied by kb multiplied by t squared. So this is one of the most general laws regarding the fluctuations of energy. So this variance of energy is related to the fluctuation of energy. Fluctuation can be understood as a standard deviation of energy from its mean value. And this is the square root of dE. That gives us square root of Cv kb t squared. Okay. So that's the final formula. So as you see, fluctuations are already with us. They have always been with us, as we have these statistical physics laws like Gibbs formula, and from this Gibbs formula we get something which can be calculated thermodynamically. So you can just measure Cv, even if you don't know the partition function of the system. We already know that if you measure Cv, you can find the fluctuations of energy in your system. This is. And actually this formula can be applied to any kind of a system. If we have an ideal gas, then we can find the fluctuations of energy even for a single particle. So let's assume we have only a single particle, and this particle can move translationally in space. So we have 3 degrees of freedom. 3 degrees of freedom. According to the equipartition theorem, the average energy of this particle is calculated as the product of the number of degrees of freedom, which is 3, as I have said previously, multiplied by kBt over 2. Now we can calculate, heat capacity of a single particle. Well, as I have described previously, this heat capacity function is actually a derivative of energy over temperature. So we can find that this is 3 multiplied by kb over 2. And then inserted it here. and get the final result. The standard deviation of energy for a single particle is given by this formula. Okay, now I have 3/2 multiplied by kBt. This is it. Actually, you can confirm this result by calculating average energy and the variance of energy of the particle directly from Maxwell distribution. And I assure you that the result would be exactly the same. Now let's discuss another type of fluctuations, which is the fluctuation of the number of particles. So let's assume that we select a certain volume inside the vessel of the gas. So this is vessel. And inside this vessel, we select a certain volume. And particles can get inside this volume and get outside. So as a function of time, the number of gas molecules inside the selected volume is a random number. Of course, if we understand everything about motion of particles inside this vessel, then we can predict how this number of molecules inside a certain selected volume will change with time. But if we don't know such information, then this number of particles will behave as a totally random number. So it will be something like this. Some kind of a step function over time. And this step function will change very abruptly, because the number of particles coming inside this volume and going outside of this volume would be, well, actually quite large per unit of time. So for calculation of this number, first of all, we need to get some idea about a distribution function for the number of particles inside this volume. So let's get with this distribution. In the ideal gas, we assume that particles move independently and randomly. That's why that if we select a certain particle, a certain molecule in this vessel and look over its trajectory over time, then this trajectory will be random and it will get into any sub-volume of this vessel, and this will happen independently of the local density of particles in that volume. In the ideal gas, this is true. But for such a particle which moves randomly in space, the probability of this particle to be found in our selected volume can be calculated as the ratio of our volume to the volume of the vessel, which I'll denote by V0. Okay. Of course, correspondingly, the probability that this particle is not inside this volume is this. And now I can do the following. So let's assume I have a large number of particles inside the vessel. This large number, n 0, can be obtained as a multiplication over number density by the volume of the vessel, V0. So we have this number of particles. And then we need to calculate the probability for a certain number of particles, n, to be found in our volume V. This problem can be reformulated in terms of combinatorics. Okay, so let's assume that we have a certain coin, and we flip this coin capital N0 times, and we have two possible outcomes, but our coin is not fair. Our coin flips on one side with this probability and on the other side with this probability. So we need to calculate the number of events when the coin have flipped n times with this probability. So altogether I have like n0 character sequences which describe the outcome of my coin flipping. So I can have the following sequence. And we have n0 such events. And all of the other possibilities. First of all, I would say that the probability for such event is different depending on the number of ones and zeros in my outcomes. Because 0 can happen more often than 1, that means that if I have a certain sequence, then for this sequence, the probability for it to appear is going to be p1 to the power of n multiplied by 1 minus p1 to n0 minus n. This is for a single sequence. But also we know that possible sequences which can have n ones in them, the number of such sequences is given by the number of combinations of n0n, and this is calculated as n0 factorial over n factorial and n0 minus n factorial. So the probability distribution for my problem is given by the following formula. P of n, the probability to have n particles inside the selected volume is given as this is a so-called binomial distribution. But in our case, we can assume that the volume of our vessel is infinitely large. We want to eliminate n zeros and v zeros from our formulas. We want to have some kind of a probability distribution which is independent of volume. And this can be achieved if the volume is very large, is much larger than the selected volume V. So if the volume of the vessel is much larger than V, then we can get another kind of a distribution from this function, which would better describe us the probability to have n particles inside the selected volume. So let's assume that V0 is much larger than V. That means, first of all, that P1, which is equal to the ratio of V to V0, is much lower than 1. Secondly, that means that 1 minus P1 approaches 1. Okay, so for our formula we have that Pn give us n0 factorial divided by n factorial over n0 minus n factorial. Okay, this is the same part as there. I'm going to do the transformations to obtain finally my distribution multiplied by p1 to the power n, which goes without any change here, and multiplied by 1 minus p1 to the power of n0 minus n. What I have here, so what do I do? First of all, n0 is much larger than n. I can say that n0 is much larger than n, because the number of particles in the very small part of the volume of the vessel would be always a very small part of the total number of molecules inside this vessel. It is almost impossible to achieve the situation in which a very small part of the vessel contains almost all of the molecules. And all of the molecules have assembled here for some reason, and almost no molecules are outside of a selected volume. This event is improbable. And there is even a problem in the homework which allows you to show that this is almost impossible. And since n0 is much larger than n, then we can calculate this difference, okay, this fraction. I can write that n0 factorial over n0 minus n factorial is actually, okay, this is n0 multiplied by n0 minus 1, so on and so forth, multiplied by n0 minus n plus 1. This equality is a consequence of the definition of the factorial. For the factorial, we have a product of integer quantities starting from 1 and ending at n0. For the denominator, we have a product, the same product, which starts from 1 but ends at n0 minus n. So all of the factors which are absent in the denominator but are present in the numerator are as follows. So we start from n0 minus n plus 1, which is the first quantity which this factorial doesn't contain, but this factorial contains, and then proceed until we reach n0. And for all of these numbers, they are actually almost equal to n0. So we can write that approximately this product is equal to n0 to the power of n. We have exactly n numbers. We start with n0 minus 0, and we end with n0 minus n plus 1. So altogether, we have n factors here. So this is 1, this is n minus 1, and here we also need to add 1. So altogether, n factors in this product. And all of the factors are almost equal to n0, so that's why I can write this. Another approximation goes with this. At first, it seems that we can change this 1 minus p1 to the power of n0 minus n with 1. But this is wrong. Because this power, n0 minus n, is very large. And you know that there are situations when the number which is almost equal to 1, when raised to the very large power, gives you something which is not equal to 1. So let me show that. You all know this limit. This is number e, which is the base for the natural logarithm exponent. So in this limit, we have, when we approach infinity, the number which approaches 1 is raised to the power n which approaches infinity, and gives me some finite value, which is not 1, but something different. Okay, let's use something similar here. Let's calculate the limit of this when we take n0 approaching infinity. Okay, here 1 minus p1 to the power n0 minus n is okay, I can assume that since n is much lower than n0, that this is approximately equal to this to the power n0. And then I can write the following, that this is actually approximately equal to e exponent to the power of minus v0 over v, and okay, it's actually v over v0 minus v over v0 multiplied by n0, because when we raised this, then it means that we have a multiplication in this power, in this exponent. And this gives us minus e to the power minus nv, where n is the number density of molecules inside the vessel, and v is the volume of the selected, is the selected volume. Okay, now we collect everything together and get that Pn is given by this formula. Pn is n0 to power n divided by n factorial multiplied by P1 to the power n. P1 is v over v0 to power n multiplied by this e to minus nv. Then we collect these two terms together and get nv to the power n over n factorial multiplied by e minus nv. Or then I can write here So I introduce new notation here, n with this line, and this is n multiplied by v. Actually, this n with this line is an average number of particles in the selected volume. And here we have a distribution. This distribution has a name. This is called Poisson distribution. And from this distribution, we can calculate not only the average number of particles in the volume, but also the variance or the fluctuation of the number of particles in the volume. Let's do it. But before I do this, I would first say that you should remember that Poisson distribution is the limiting case of a binomial distribution. This is what follows from our derivation. We have started with binomial distribution and ended up with the Poisson distribution when we go to the limit, when the number of particles becomes very large. Okay, then let's calculate the average number of particles. It should be sum over this n multiplied by n to the n divided by n factorial multiplied by e minus n average. This gives me the following. We have a sum over n. Okay, we have this sum. This is sum over n. And here we have n minus 1 factorial, because the factorial contains the product of all integer numbers starting from 1 to n. And we have n here, and that means that in this product, n is being eliminated. And after that, we have a product of numbers from 1 till n minus 1. That's why we have n minus 1 factorial. And then we can take this from here, and we have a sum over n. Okay, and this is actually equal to n, this n with this line. Okay, as I have said previously, n with the line above it is an average number of particles. Here is the proof. So this notation is not chosen randomly. Actually, this is another notation for an average value or mean value. And this sum is actually equal to 1. It can be easily seen, because this part of this sum is a Taylor expansion for the exponent. This is actually a Taylor expansion for the exponent. And this is Taylor expansion for e to the power n with line. And here, multiplied by e to the minus the same power, after we take a product, that means that in the exponent we have sum of exponents, n minus n, which give us 0, and e to the power 0 is 1. As should be expected. So this probability distribution is already normalized. This probability distribution is already normalized. So if we calculate the sum of Pn over n starting from 1, or starting from 0 actually to the infinity, then we will get 1. And this is what happens. Actually happens here. Now let's calculate mean value of the squared number of particles. It's slightly different. Okay, let's see what happens here. Actually, first of all, we do the stuff which we have done here. Okay, we have sum over n of now we need to do something to calculate this quantity. So let's look. So here is this expression, and what can we do to calculate this sum? Actually, we can do something similar to what we have done with this partition function, and we have done derivatives over some parameter here. We can do derivatives over parameter. And as a parameter here, we have this n with this line. This is a parameter of our distribution. So let's see what would happen if we take a derivative over parameter of distribution. Okay, so it would be better if we introduce this function z, which is n to the power n factorial. And now let's try taking derivative over this function. So we already know that, okay, this is sum over n, and this function actually is equal to the e to minus n average. Okay, this is e to the n average, because if we multiply it by e to the power minus n average, we would get 1. Okay, let's see what happens if we take derivative. dz over dn average. Okay, this is a simple function like x to the power n over dx, and this would give us the following sum. This. Okay, as we can see, this function is actually, this sum is actually a sum which has occurred here. So after we take this derivative, we get sum for n starting from Okay, here we have this one. Or we can actually say that in other words, we can do the following transformation, that this is sum of n over n average multiplied by n average to the power n over n factorial. As you see, this should be average of n over n with line multiplied by e to the power minus n. Because this is a probability multiplied by e. Okay, so this is probability multiplied by exponent. So I have partly here, I have an average of this quantity multiplied by this exponent. So I take this exponent out of the sum, and what remains inside the sum is actually an average of this quantity, n over some constant. And after I take average, this is average n over some constant. And if I take the derivative from the final expression, I get the same result as I have obtained previously. Okay, so this means that we have some kind of a productive method to calculate averages in Poisson distribution, and then we need to make another calculation of derivative. So we need to calculate a second derivative of this function z. And this second derivative would give us something related to the variance of the number of particles in the selected volume. Okay, let's do this. So the second derivative. This is actually a sum of over n of 1 over n factorial multiplied by derivative over the constant Okay, so after I take this derivative twice, I get n multiplied by n minus 1 over n factorial multiplied by this over this squared. Okay, this is it. That's what I get. And then I can express it through these probabilities. So I can write that this is actually a sum over n of n times n minus 1 over n squared multiplied by Pn, this probability which comes from Poisson distribution, but we don't have exponent here. That means that this is a probability multiplied by exponent, by this exponent. So I can write, similarly to the previous derivation, I can take exponent out of the sum, and inside the sum I have n times n minus 1 over n with line squared multiplied by Pn. This is actually average of this number. So that means that I have here E to n with line multiplied by average of n times n minus 1 divided by this square. But as we know that if we take two derivatives of the exponent, we get exactly the same exponent. So this equals to the same exponent. That means that from this expression I get that average of n squared minus n over this should be 1. Let me see if there is any mistake here. So I take this derivative first, I get n, then I take second derivative, I get n minus 1. And then I have the same sum, but for n equal to 1 and n equal to 0, this equals to 0. Okay, I have this average. Well, nothing seems wrong here. Okay, but actually, from this we have the following, that average of n squared minus average of n is equal to this squared. And actually, as I have proven previously, this average of n is equal to my constant. So that means that average of n squared is equal to, okay, and from this I can calculate variance. The variance for the particle numbers is found as the difference between average of the squared numbers of particles, the average of squared numbers of particles minus squared average. So the order of operations is what matters here. If we take squared before averaging, then we get different value than when we take squared after the averaging. And then after I insert all what I know inside this expression, I get that the variance of the number of particles is equal to the average number of particles. This is one of the important properties of the Poisson distribution, that its variance equals to the average number of particles. And from this we get that the standard deviation for the number of particles which is calculated as square root of the variance, is square root of the average number of particles. And relative fluctuation is the standard deviation divided by an average number of particles gives us 1 over square root of an average number of particles. This is the main result here. The fluctuation for the number of particles is given by this, and the relative fluctuation is given by this. Although the initial distribution looks quite complex, the initial Poisson distribution is asymmetric. If, let's say, an average number of particles is equal to 2, then the Poisson distribution gives us some kind of an asymmetric function, because it's impossible to have the number of particles below 0. That's why this distribution is always asymmetric. But nevertheless, it has this important quantity, this important property, that the standard deviation is equal to its average. Okay, let's continue. Actually, this 1 over square root of n would always appear if we study the fluctuations of thermodynamic properties. And the reason is that for the fluctuations of thermodynamic properties, is that mostly thermodynamic quantities describe something which is related to a very large number of particles. And if the property is related to something of a large number of particles or large number of samples, then we fall under the conditions of the central limit theorem. Central limit theorem. It's a theorem from the probability theory, which states, in short, this theorem states that if we have some random quantities, A0, A1, and so on and so forth, and An, and we have large number of these quantities, and we consider a new random quantity which is defined as an average over these n quantities. Okay, we start from A1. As an average, then central limit theorem says that this quantity A has a Gaussian probability density function, or it is distributed normally. And A has normal distribution, and moreover, we can calculate the average value of A and its standard deviation using the following formulas. Okay, for the standard deviation. So whatever the probability distribution of the initial quantities A0, A1, A2, and so on and so forth, An, as long as the probability distribution is the same for all of these quantities, then for an average value over n of them, then this has normal distribution which has the same average value, but the standard deviation is equal to the standard deviation of one of these quantities over square root of n. If we consider the quantity which is not an average, but is a sum of these n quantities, as what happens for energy and entropy and other additive quantities in thermodynamics. So let's say if A, capital A, is equal to sum of all of these numbers, then average of capital A is calculated by multiplication of n by an average of any of this number, and the standard deviation is calculated is square root of n multiplied by standard deviation of any of these numbers, of a single of these numbers. So as you see, we have something very similar to these properties or to these expressions which we have determined previously for the Poisson distribution. And actually we can derive the same expression using the central limit theorem. But the central limit theorem applies to the conditions, okay, here, when sigma A is much lower than average of A. So this means that if we can consider the Poisson distribution even for a small number of particles, if the number of particles on average inside the selected volume is very small, like 2 or 3 or 10 or 0.1, then the following derivation, which is based on the central limit theorem, requires this. That is because central limit theorem is a more general statement than any statement regarding the number of particles in the selected volume. This is a more general law, and that's why we have some kinds of limitations imposed on this law. So first of all, if you want to do this calculation, let's do the following. Let's consider one particle, one molecule. Okay, the probability for this molecule to be outside the selected volume is 1 minus V over V0. To be inside is V over V0, inside the selected volume. And then we construct a random number which is 0 when the particle is outside, or equals to 1 when the particle is inside. Inside the selected volume. So here we consider the same physical problem when we have a vessel and we have a selected volume in it, and the selected volume is much smaller than the volume of the vessel, but we know for some reason that the standard deviation for the number of particles inside the selected volume is much lower than the average number. So we can be sure that the average number of particles inside the selected volume is large. This is the applicability condition for the central limit theorem. If we know that average number of particles in the selected volume is much larger than 1, then we can apply it. And let's check the result. Okay, so we have this xi quantity for the molecule number I, and the number of particles inside the selected volume is actually equal to the sum of all of the xi, starting from the first molecule and ending with the last one, which is the molecule number n0. So from the central limit theorem, we obtain that the average number n is equal to the average number of xi multiplied by n0, and here the standard deviation for the number of particles inside the selected volume is equal to the sigma xi multiplied by what? By square root of n0. Now let's get to calculations. Since we have only two possible outcomes for all of the xi, all of the calculations become quite simple. Xi average is equal to 0 multiplied by P0 plus 1 multiplied by P1, which is exactly equal to P1, the probability for the particle to be found in the selected volume. And after we insert this into this expression, we get P1 multiplied by N0, which is N0 multiplied by V over V0, which is number density times V. As in the previous calculations, so we had this n with line, and n with line is actually n multiplied by V. Okay, for the standard deviation, sigma x, we have square root of average xi squared minus xi average squared, and this, okay, let me get to the other blackboard for the calculation of this quantity. Okay, we already know this one. What remains is to calculate this one. Okay, this one is P0 times 0 squared plus P1 times 1 squared. Well, actually it's exactly equal to P1 again. So this quantity is equal to P1 again. But this average is equal to P1. And when squared, it gives us P1 squared. And we can neglect this P1 squared with respect to this P1. So this is actually square root of P1, because P1 is much lower than 1, and that's why P1 squared can be neglected. So finally, for the standard deviation for the number of particles in the selected volume, we get square root of N0 multiplied by P1. Again, P1 multiplied by N0, the same combination. And this is actually again equals to square root of NV, which is square root of the average number of particles in this volume. So these results, which we have derived previously as exact results, can be obtained as a consequence of the central limit theorem under the condition that this number is much larger than 1. Also, we can say that the Poisson distribution becomes normal when the average number of particles in the Poisson distribution approaches infinity. So when it gets large, then Poisson distribution becomes normal distribution. Thus, I can say that we have established the following relations between different distributions. First, we have shown that binomial distribution at some limit becomes the Poisson distribution. And the Poisson distribution, under an assumption that n average is much larger than 1, becomes normal distribution. But please keep in mind that central limit theorem and its consequences are actually much more general than Poisson distribution and can be applied to any kind of thermodynamic quantity, not only to the number of particles. The same is valid for volume, for pressure, for temperature, for an average energy, and for any kind of thermodynamic quantity. We have normal distribution. So if we measure the internal energy of the system, then we will find this probability distribution for the internal energy of the system. If we measure pressure, if we measure volume, then everything would obey the same normal distribution. This is the main reason why this is valid, is that thermodynamic quantities are quantities which aggregate the state of very large number of particles n, and due to the central limit theorem, any such quantity would have normal distribution. Okay, now let's proceed further. And discuss fluctuations of volume. Previously, we have discussed fluctuations of energy and fluctuations of number of particles. Now let's discuss fluctuations of volume. First, I would like to make some disclaimer. The discussion about fluctuations of volume would be done somewhat tentatively. So it would not be as rigorous as a discussion about the fluctuations of number of particles or fluctuations of energy. It would be quite tentative, but nevertheless, the final result will be correct. And I believe the rigorous introduction to fluctuations of thermodynamic quantities should be done in the course of theoretical physics and statistical physics as a part of such course. That's why I allow myself to do some tentative introduction to the fluctuations of volume. Well, first of all, I would start with Gibbs distribution for a pendulum. The problem which seems completely unrelated to the problem which I want to discuss, it would give us some hint to how calculate fluctuations of volume. Okay. So let's assume that we have a pendulum and we have a gas environment which can be found all around the pendulum. And the energy of the pendulum as a macroscopic system can be written as follows. Where h is an elevation of pendulum above its equilibrium position. Well, we can calculate this h as a function of displacement of pendulum from its equilibrium position. H can be found as, okay, if we have the thread length equal to L, and this equals to x, then this h can be found as L minus square root of L squared minus x squared. And since we discuss thermodynamic fluctuations, it's obvious that this displacement x is much lower than L. And that's why we can use some expressions designed to calculate some functions when we have small changes in its arguments. So first we take L out of the square root, and inside the square root we have something which is very close to 1 but slightly different. And then we make use of the following expression, which is varied when its argument is much less than 1. Okay, it can be seen that this expression actually the first two terms in the Taylor decomposition of this, Taylor expansion of this function. And you can write here, this is 1 minus 1, and here minus x squared over 2l squared. This gives me x squared over 2l. I get it into this energy and get mv squared over 2 plus mg x squared over 2l. And then I can apply Gibbs distribution to this energy function, because Gibbs distribution assures us that the system can be found in the state with some total energy E with the probability which is proportional to the probability for the system to be in the microscopic state with some energy E is proportional to exponent of minus energy over kBT. Now let's assume that we discuss only the displacement. So we want to find the probability distribution for the displacement. Okay, so that means that the probability to have some displacement x is proportional to minus mg x squared over 2l kBT. And as I have said previously, when we have any kind of an energy term which is quadratic with respect to either the velocity or the displacement or the coordinate, that means that according to the equipartition theorem, average energy associated with this motion, so here average of mgx squared over 2l should be equal to kBT over 2, according to the equipartition theorem. And from this we can find the fluctuations of the displacement of our pendulum. So there are some displacements which happen due to the presence of environment and due to the collisions of our pendulum with the molecules of gas. And these displacements are very small, but nevertheless they obey this condition. Okay. Well, please note here that here we have an oscillator, and one of the applicability conditions for this formula is that kBT is much larger than the quantum of energy in this oscillator. This quantum of energy contains an angular frequency of our oscillator, and for the macroscopic oscillators, well, this omega is of the same order as, let's say, 1 hertz. So one reciprocal second. And if this is valid, then actually for room temperature and even for low temperatures, this condition is always satisfied. That means that we can apply equipartition theorem to this oscillator. Next, let's discuss the fluctuations of volume themselves. So this problem is a sort of a hint. Well, first of all, if this system is not a pendulum, but an oscillator on a spring, then nothing would change. But except for this mg over 2l, we would have the spring constant k in that formula. So we would have mv squared over 2 plus kx squared over 2, where x is a displacement from the equilibrium. And again, we do the same calculation and find the displacement. Now, the next system which we are going to discuss, let's say that we have a certain volume or it can be gas, or it can be some fluid, some liquid, which contains a certain number of molecules, and this fluid is surrounded by thermal environment. So we have some kind of an external pressure P0, temperature T0, and some number of particles which surround our selected volume of fluid. How do we calculate the fluctuations of volume of this fluid? Okay, we know that there is some quantity which is called compressibility. So here we discuss isothermal fluctuations. So we consider isothermal compressibility, K, which is 1 over V of minus derivative of volume over pressure at a constant temperature. So if the volume of this fluid is lower than its equilibrium volume, then the pressure inside this fluid becomes higher than the pressure of the surrounding environment, and this fluid will be out of an equilibrium with the surrounding environment, and it would expand. And this fluid would expand. And vice versa. If the volume of the fluid is larger than the pressure inside this fluid, average pressure is lower than the pressure outside, and this fluid would contract. So that means that if there are some fluctuations of volume, then this bubble of fluid is found in the process of oscillations, when the volume is expanded and contracted, and it follows. So, and we have a system which is very similar to oscillator or to a pendulum. We just need to write an energy of this system. The potential energy associated with these expansions and contractions is found as follows. So we need to calculate mechanical work, which needs to be done in order to compress the fluid. Okay. So mechanical work is calculated from the equilibrium volume V0 to the final volume V as minus P dV, okay, minus delta P dV. So we have external pressure, so this delta P is a pressure difference between the pressure inside this fluid and the pressure outside this fluid. It's delta P multiplied by dV. And when dV is negative, and if we have a process of contraction, that means that we need to apply additional external pressure to contract our fluid. And then dV is negative, the work should be positive. The work should be positive. So I write here minus delta P multiplied by dV. Okay. Then according to this compressibility coefficient, my delta P as a function of volume can be found as minus 1 over V0 multiplied by V minus V0. Okay, so for the dP. So here we apply external pressure and see how the volume has been changed. So I just written something wrong here. So for the dP I write minus V0 multiplied by, or actually divided by K, and divided by V minus V0. So let's look at this expression. So if, oh well, something wrong is here again. So delta P, okay. Now finally I can write it correctly. I have minus V minus V0 over K. Okay, this is the, if the compressibility coefficient is larger, then that means that this liquid can be easily compressed, and that means that lower amount of the pressure change would create larger difference in volume. Okay, so now everything becomes fine, multiplied by dV. And here, when we compress the liquid, then V is lower than V0, but multiplied by this minus give us some positive quantity, and dV here, V is, this positive and this is negative, but V is lower than V0, and that means in this integral we have positive integral after we calculate it. Okay, so now we do this calculation. This integral is minus V squared over 2 minus V0V over V0K, and the difference between the final volume and the initial volume. Okay, at the final volume we have this. At the initial volume we have this. Okay, then after we collect all of these terms, we obtain the following expression for this potential energy. The potential energy is equal to, actually, V minus V0 squared over 2 V0K. Okay, you can check that this expression indeed can be obtained from this formula. Okay, and actually what's interesting here, that this expression is always positive. So either when we increase the volume or decrease the volume, the potential energy, when it's different from this equilibrium, but from the when the volume is different from the equilibrium volume with 0, it becomes positive. And now again we have a quadratic function as a function of volume, and then we can write this average energy is, according to the equipartition theorem, is equal to kBT over 2. And from this we can find our fluctuations of volume. Okay, we cancel out these numbers here, and then we find the standard deviation for the volume as follows. This is kBT multiplied by V0 by an average volume and multiplied by K, where K is an isothermic compressibility. And now we take also a square root. And please note that 1 over square root of n law is already present here. If we increase the volume, then relative fluctuation which is equal to sigma of V over V0 is proportional to some constant, which is kBt, multiplied by another constant, which is independent of volume. This compressibility is the physical quantity which is independent of volume of the medium, and divided by V0. So that means that the larger the volume of the system, the lower the relative fluctuations of volume are. Okay, another fluctuation I would like to show by the end of this lecture is the fluctuations of volume at a constant energy. At constant energy. So we can, for example, surround our system with some kind of a shell which is impenetrable for heat and which doesn't allow any heat exchange between our system and the external environment, and then again calculate the fluctuations of volume. The internal energy would be exactly the same. Instead, with one exception, we need to replace the isothermic compressibility K with an adiabatic compressibility. So adiabatic compressibility is defined as 1 over V multiplied, again, minus dV over dP at constant S, which corresponds to the adiabatic process. And there is a common equation, or not expression, or identity in thermodynamics, which relates adiabatic compressibility to the isothermal compressibility, and this is as follows: K adiabatic over K isothermal, which is equal to dV over dP at constant S over dV over dP at constant T. And this is actually equal to Cp over Cv, the ratio between heat capacity at constant pressure to the heat capacity at constant volume, which is sometimes called adiabatic exponent. dV over dP. So to illustrate this equation, I would consider the adiabatic process and isothermic process for the ideal gas. The isothermic process is described by an equation that PV is constant. Okay, this is an example which shows this expression is valid for any kind of material, but I would show it on a particular example of ideal gas. Okay, it's actually Cv over Cp, which is 1 over gamma. So here the adiabatic process has the formula Pv to the power of gamma is constant. And as the gas expands, its temperature decreases. So that's why the pressure changes are greater for the same changes of volume. And that means that if the pressure changes are greater, that means that we need to have lower quantity here than here. So this is lower than 1 and equals to Cv over Cp. And you can check that this is actually valid. Volume in the adiabatic process is proportional to the 1 over P to the power of 1 over gamma. And that means that dV over dP divided by volume, which is actually a logarithmic derivative of volume, should be equal to minus 1 over gamma. The same quantity for pressure is which is proportional to -1/gamma, and the same for the pressure for the isothermic process is given as follows. The logarithmic derivative of volume for the isothermic process. In this we have volume which is inversely proportional to P, and then we inserted here the logarithm of V is some constant minus logarithm of P, and here, okay, it should be minus pressure over gamma, and here it should be equal to minus pressure. So from these two expressions it can be easily seen that this ratio is indeed below 1, and adiabatic compressibility is somewhat lower than isothermal compressibility. That's why the fluctuations of volume at a constant energy should be lower than fluctuations of volume at constant temperature. Okay, with this I would like to end my lecture, and thank you.